Welcome back. This is number 6 of the series. Last time we were working on the C program to generate prime numbers, and I've got a pretty good version of it going here. So let me describe what I did. One, I'm assuming that you're reading the Kernahan and Ritchie, or you know C, or you've got a bunch of books on C, went to archive.org and have downloaded or looking at them or reading them and checking them out, all that stuff. So we had 2 includes right at the start of the program to include 2 headers. One of them is standard IO, that's so I can do a printf, and then I had standard lab to use the exit function down here at the bottom. First thing you do in programs before the main is to define functions in a form called function prototype. You specify what value it returns, if any, the name of the function, and this one's going to be isPrime, and its purpose is to take a 64-bit integer as its input, as its parameter for one parameter, and determine if it's a prime and return an integer value. It's going to return a value of 0. If the value you give it is not a prime, it will return a value of 1 if the number is prime. Main routine, we use a standard C function to look at the command line and determine how many arguments there are, and then place them in this array of pointers that points to memory buffer where the values are stored in character format. The input from the command line is going to have 2 integers, a starting integer for the range that I want to look at, and an ending value. So that'll give me the entire range. I'm going to start with a starting value and test each odd number to see if it is a prime number. Every time I find one, I'm going to do a count. I'm going to add to the counter, which is called count. I could have called it counter, but let's keep to small words. And when the counter gets to 8, I'm going to output a new line because I want to keep the lines to 8 numbers per line. I don't have to do that, but that's what I chose. You just pick your value. I'll show you later. Remember, I did the idiot test here to see if the argument count was 3. I guess I ought to check to see if the argument count is greater than 3, but if it is greater than 3, well, I'm just going to ignore the rest of the things that you put in there. So you could put a comment in there. We'll do that. Let me make a note. Comment. Okay. So here I do a string scan, which says take the string. This is the second field in the command line, argument vector 1, and I'm going to convert that string to a 64-bit unsigned integer and store it in start. So that's my starting value. Then I do the same thing for the second number and put it in end. And remember, I had, for the first part of the program, when I was just writing a segment and then I would test it, here's the 2 prints to get the starting and ending value, but I'm commenting them out because this is a program and we're going to use it to output the values to a file, and I want no stray information in there. I want only the prime numbers. You'll see that later. I do a check to see if the starting value is less than 23. I'm just going to go ahead and output the first 8 prime numbers. And I do that with printfs. I print out the number followed by a space here, and I output 2, 3, 5, 7, 11, 13, 17, and 19. That outputs, because there's no new line in any of these control formats, these will all be contiguous on one line separated by a space, and then I print out a new line. So this will go to the next line, get ready for the next numbers that I calculate. Since I output all these less than 23, I change start to 23. And now we're going to start at 23 and go to the end to check for primes. There is a possibility that you're not thinking when you start the program up and you give it an even number. I don't want to do even numbers, so I'm going to kill off the program. If the starting value is mod 2 equal to 0, that means it's an even number. I'm going to print out, sorry, starting integer must be an odd number, new line, and then I exit. So let me go down here, and here's my main part of the program. I set the count equal to 0. No matter if I skip the first part here to print out 2 through 19, this means that the starting value's big, and I'll just start testing the numbers. To test, I start with the starting number. Okay, I check to see, am I through yet? And I'm going to go to the end. Well, end number may be odd, maybe even, it doesn't matter. I'm just going to go up to the range. If start is less than end, then I go through here. And the nice thing about VI is VIM is when I put the cursor on a starting brace, it highlights the ending brace. So this will show you a block of instructions that are executed for every time you do the for loop. I check to see if is prime test true or false. And the way an if statement works, if the argument is 0, then it's false, and I will not do what follows the if statement. If it's non-zero, in this case, if test is a prime number, then I'm going to do this block. And what I do is I print out the number, followed by a space, increment the count by 1, and then I check to see if count mod 8 equals 0. If it is, then I've output 8 numbers on a line, and I just generate a new line. And I do this for the range, start to end, for all the odd numbers. Because I did a test, remember, start is odd, prime numbers are odd, and I increment by 2, checking every odd number that I want. When I get through, there is the possibility that the last line may only have 3 or 4 numbers in it, so I'm going to generate a new line. It's just the way I want to do this. All right, now here's my function. Okay, is prime takes a 64-bit unsigned integer, variable name n. I've got a loop variable I. And then I check to see if the number is a multiple of 3. If n mod 3 is equal to 0, then it's impossible for that number to be a prime number, so I return 0. After that, what I do is I start this loop with I equal to 5. Make it unsigned long. And I did this program 64-bit so that I can go to a very large number. In fact, the largest integers that I can do in an orange pi 5 plus. And if you're not going to do anything larger than 2 to the 32 minus 1, then you can make them all just int. Here's an exercise. Will the program for n less than 2 to the 32 minus 1, will the program run faster with a 32-bit int than a 64? This is an architecture, computer architecture, EE computing science question as to will programs run faster with a smaller int or bigger? And it's either, well, it's a question of a number of things. I'll leave it and come back to it maybe later. On the for loop, I'm going to go and test only the odd integers less than the square root of n. I times I is I squared less than or equal to n. Take the square root of both sides, and this is going to check to see if I is less than the square root of n. Because mathematically, draw you a little line and figure this out. For any n, if there is no factor less than the square root or less than or equal to the square root of n, then there's no factor. Because if there is a factor, the other term is greater than the square root of n. Okay, if you did your study on primes, it turns out that prime numbers are either less than 1 or greater than 1 of every factor of 6. So all I have to do is check numbers on either side of 6 to the n, or m, where that's a different integer than n. Okay. I gotta quit saying okay. Sorry, I apologize. It's a bad habit. By doing this, I speed things up. Again, you check this out because I want to keep this lecture, short. I can explain everything in detail, but it's a waste of your time and mine. What happens is for every 5, 7, 9, 11, etc., 5, 11, 17, whatever, I'm going to go and check to see if n mod I, if the number that I'm checking to see if it's prime has a factor I. If it does, return 0. Then I check one on the other side of I plus 1, that'll be the odd number on the other side of 6 to the m. If that is equal to 0, then n is a factor, so it's not prime, return 0. And it'll turn out that if a number is not prime, most of the time this will get through pretty quick for the non-prime numbers. For prime numbers, I got to go up to the square root of n. Now, the reason why, if you check a lot of programs on the web, they will do a check here for. I'll show you. Let me yank this. They will do this. They will do I less than or equal to square root of n, and maybe they will cast that to floating point. There is a possibility if n is a perfect prime, say n is 225, square root of 225 is 15. So 225 is not a prime number. But there is a possibility, now maybe not for 225, but some large integer, you do the square root of it, and it comes out to be 14.99999. That means they did not check for 15 squared, and it shows the number to be prime. Just a note. If it fails all this test, then it is a prime number. I'll return a value of 1. I'll let you stop the video, look at this, type it in. I don't know of a way. I'll try to figure out later if there's a way I can share things with you. I know there's one way. I have a web page, but I don't know if I want to use it. Maybe I'll create a new web page. Stay tuned. Operators are standing by. Now I'm ready to test the program. Let's compile it. I want to do a test on the C compiler optimization. Compilers have optimization levels. Says, can I take your code and improve it and make it run faster? I'm going to output this to a file called primes. That'll be my executable. My source is going to be primes.c. Compile it. Now let's test it. Dot primes. Oh, I've got this thing set up. Let me copy. Well, I'll just copy primes to my bin directory, which primes. Okay. Whoa. Wait. Let go. Dollar path. Huh. Tail is a routine that shows me the last 10 lines of a file. I thought I had this. Yes, it does. Huh. There's something wrong. Okay. That's why I'm going to talk about something at the end of this video. Source dot execute it. Now, echo dollar path. Hopefully you're reading the book on shells. That added it. There is a problem with Ubuntu. We'll come back to it. Okay, I got that fixed. Which primes? It's still. Well, let's exit that. Let's start another shell. Which dot which which primes. Okay, that's the problem. Oh, no, I'm sorry. Project dash 001. I'm okay. CP primes to tilde slash bin. Which primes? Not working. Well, let's test the program. So there are all the primes between 2 and 1,000. Let's see how long it takes. Wow, it took 0. The clock is not fast enough to. This takes less than 1 millisecond. So let's do a bigger one. Let's time primes from 2 to 1. Let's go to 10 million. Ready? 2 seconds. 2.3 seconds. The user time is the amount of CPU time that you use to execute the program. The real time is that time plus the delay between when you hit the return, the shell figures out what to do, passes it to the scheduler, and all the stuff that follows. System time is 0.267. That's how much time system overhead to load it into memory, etc. And the rest of the time is I/O time. and other stuff. I don't want, it's kind of nasty to look at all that stuff, so let's go re-execute the program again, but this time let's output to 001.out. This is the first run I'm doing, so let's send it to out. And it's 2.3 seconds. Now, I don't want to look at all the files, so there's two routines. I already showed you one, but head 001.out shows you the first 10 lines of the output. So that gives me the prime numbers 2 through 409. If you want to look at the last 10 lines, if head gives you the first 10, tail must give you the last 10. So this shows me that everything up to 9,999,991 is a prime number. Let's check that, because you may say, well, that is impossible. Let's go to the web. I got this thing set up there, but let's do something now. Oh, no, I got it set up where I want. There's an online site called wolframalpha.com. Wolfram Associates, or whatever their company name is the group that does Mathematica. So I want to go here and I'm going to say is, paste the number, prime. And the result says input is something, a prime number. It made a proper sentence out of it. Result is that 999,991 is a prime number. Also, this is neat. I consider neat. There's an ISO standard that says if you do not want to put commas, as we do in, I guess, English countries, and some cultures want to put a period for separation between every 3 digits. But what they do is the ISO standard says if you put an extra space between every 3 characters, it makes the number easier to read. And it does. Okay, there I did it again. Now, I want to benchmark, or I want to look at the power consumption on the Orange Pi 5 Plus. I purchased and received yesterday in the mail a USB-C, a USB-C power module. I powered down the Orange Pi 5 Plus. I'm gonna call him OP5. I powered down the OP5, inserted the USB-C power module. I got this thing off of eBay. Inserted it in the line between the wall wart, the power supply, and the board. And here's the measurements that I have so far. Because in the Geek Pi enclosure, the fan is connected to pins 2 and 3 of the 40-pin GPIO. When the power module, when the power supply is on, the fan is on, whether the computer is running or not. And the fan draws 50 milliamperes, 0.050 amps, at 5.2 volts. So that means the fan is consuming 2.26 watts, just a little over a quarter of a watt. So that's part of the power budget. If I turn the computer on, or when I turn the computer on, the current consumption goes to 1.1 ampere. That means that the fan plus the computer is running at 5.1 volts with 1.1 amp current. That means it's 5.6 watts. That is a very small number. There's a lot of stuff just sitting around that consumes 5.6 watts easily. Small, well, not small, but, well, there's just stuff. I'll figure that out. The idle temperature with the system powered up, the idle temperature is 35 degrees Celsius. And I think my room temperature, well, I know it's around 75 degrees Fahrenheit. Let's do this. Let's say 75 degrees Fahrenheit is 23.9 degrees Celsius. So that's my room temperature. Don't you just love the web? There is a monitor. Remember what I showed you, the load thing? Let's do a top. Top showed us that here, see, the system's only been up three and a half hours because I've been trying to chase down a problem. The load average is 3.34 because I'm running the simple screen recorder. All right. It shows CPU percentage at 1.6%. That means that it's using more than one processor to run. Processing video is a number crunching activity. So this is top, but there are two other utilities for looking at what's going on in your computer. One of them is called HTOP. Now HTOP shows a graphical thing. There are three parts here. One of them, the upper right, shows me that the host name is Colossus. There are 116 processes or tasks in the system. One of them is running, now 4. So some of them run, shows me my load average. The left-hand side shows CPU activity per CPU. There are 8 CPUs. Now this utility is wrong because the CPUs are numbered 0 through 7. And shows me how much memory I'm using, etc. And then the name of the task. Looky here. The simple screen recorder shows up with this utility in a whole bunch of separate tasks with separate process ID numbers. So there's a problem with this thing. I don't like it, so I'm going to quit it. Let's go quit it. I need an F10. Quit it. Next utility is BTOP. BTOP shows in the top panel on the right-hand side the 8 processors C0 through C7. And there's a timeline. I just started it, so this line will just creep left. Each one is a 2-second interval, 2,000 milliseconds. And you can increase this or decrease it. I'll just leave it at 2 seconds. Shows me that the processor is running at 1.8, a processor is running at 1.8 gigahertz, and that is the upper limit of processors 0, 1, 2, and 3. Processors 4, 5, 6, and 7 can run at 2.4? Yeah, 2.4 gigahertz. Bottom here shows load average 3.37, etc. Light top and HTOP, we get the programs or processes running. Over here is a column which shows who's running it. And even though I'm logged in up here as Chuck Adams, there's an Orange Pi routine running. And that's a problem. get back to that. And the simple screen recorders, this shows 20%. So I'm gonna leave this running. It doesn't take too much CPU power itself. Oh, B-top right here was taking 0.1%, so it only samples once every 2 seconds, so that's pretty efficient. I'm ready to see what happens when I get 8 processes running, or 6. Let's run 6 because I need the screen recorder and everything. I didn't finish my little optimization stuff, but if I compile this thing, up the optimization, I will still find that the time still 2 seconds. So my code for this program, and it's so simple that the compiler can't do anything to increase it. I want to run 6 copies of the program, but I don't want to type all that stuff in, so I'm going to create what is called a script. The script shows the lines, or each command I want to run in order I want to run it. Okay. So I'm going to compile the program again. Then I'm going to run primes from 2 to a huge number. Goes to 1 billion. Okay. Then I'm going to run, and I don't want to see the output, so I'm going to write it to a file, 001.out, and I'm going to put it in the background, which tells the shell, start this program up, and then put it in the background to run, and then come back to the shell and take the next command. The next command says, so let's run primes again, but start at 1,000,000,001 and go to 2 billion, and output that to I'm going to call it 2.out. Also do that in the background. And again, so this is 6 copies of the program that are going to be running simultaneously, and then I exit the shell. Later on I'll show you some other stuff, but this is just to get you started. This does 2 things. 1, you don't have to do a whole lot of typing. 2, if you make a mistake, you can correct what's wrong with primes or whatever program or anything that precedes this and redo it. To execute the shell, I can make it executable. Chmod, change the mode, +X, run.shell. Now when I do an ls-l, you'll see that 001.out is text, primes is an executable, primes.c is not executable, and then run.shell is executable. So just like primes, I can execute the shell by doing /run.sh, hit return, and it comes back immediately, and you say, oh, I wonder if that's working. Well, let's look at what processes are running. To do that, we use the ps command. Do a man on ps, and it says report a snapshot of the current processes. One note on man pages. You'll notice at the top it says ps, all of them are in capital letters. That's the name of the user command. And then there's a number. The number is from the early days of Unix at Bell Labs. Kernighan, Ritchie, and Thompson, and the other people that were using and creating programs for Unix would create this manual page, and there were several manuals. Manual 1 2, 3, I think there were at least six manuals. I'll have to go back to archive.org and see if some angel in the universe put copies of the AT&T manuals up there. If they are not up there, and you can find a copy, try to find a way to get it scanned in and put up there. Let's save the universe. All right, part PS. And voila, I've got 6 copies of Prime running. One of them has a processor ID. That's a number assigned to every process that goes into to be executed. 8572, and they're all in a row. So they're running. Let's go back to where's my monitor program? That's not it. Here it is. Well, everything's red because now, at the time that I started the 6 processes at this time, all the CPUs, all 8 of them, have gone to 100%. Because I've got 6 copies of Prime running, plus I've got the screen recorder running, and it's taking up a bunch of stuff. Now, this program, I don't know who wrote it and what they were thinking of. This thing here where it says my copy 8573 of Primes, which is going to start at 1 billion and go to 2. I don't have the full line listed there. Being run by me. It runs in memory of 728K. Is only using 12%. Well, 12% is 1/8 of the total. It would be nice to do the percentage of how much time is this using on one CPU. So for the advanced students, I want you to recreate this in C. I bet you this is written in Python, but I wouldn't guarantee it. Rewrite this program or find the source if it's available and correct it to do percent CPU usage in terms of one CPU. The thing I like about this program over the HTOP and even top is the graphical display here, but it shows you the CPU temperature here on this line. If you can see where the cursor is in the upper right, CPU, 99%, whatever. The temperature of the processor has now gone to 52 degrees. And it looks like for this system, there's only one thermometer, and it's the temperature of the chip total. So we went from 30, when the system is just idle at room temperature, the temperature of the processor is 35 degrees Celsius. Now it's up to 52 degrees Celsius. I can tell you from experience that is an excellent number. Most silicon processors, Intel, AMD, and the others will, and I'm assuming that the Rock chip will run without too much trouble up to 100 degrees Celsius. One of the things that we may do in this course is see if we can find a way to see if the system throttles, that is, reduces the CPU speed to keep it cool. What happens is on the Intel, if the processor heats up to 100%, it throttles it, that is, turns down the CPU execution speed from 1.8 or 5.5 gigahertz down until it cools off. Back in the days when I was teaching, I would tell my students, the ultimate computer is going to be a hairy, smoking golf ball immersed in liquid nitrogen. One, it'll be hairy because we need all the I/O. We need the I/O for graphics, we need the I/O for input, we need the I/O for disk, and we need the I/O or wires for memory, for the bus. It's going to be smoking because it's going to be overclocked. And when you overclock a CPU, first thing that hackers and everybody want to do when they get a new computer is overclock it. I am not going to overclock this thing. That's for you to decide if you want to. Can you overclock it? Can you get the temperature greater than 42 degrees or 52 degrees? Can you get it close to 100? Somebody's always going to do that. Now, the faster you clock gates and silicon, the hotter it gets. But also, remember I put the Orange Pi 5 Plus in a Geek Pi case. It has a small fan and the heat sinks. I used the heat sinks that were provided by the case, the little small ones. I see videos where people go in there and put in an oversized heat sink and fans, water cooling. Let's just go put it in a bath of liquid nitrogen. Probably won't work, but because it's not enough heat. But anyway, check. For me, this is good enough. It's not going to get any hotter unless the temperature goes up. Now, outside the temperature is around 100 and something right now, and it goes to 118. We're in the middle of summer in environmentally stressed planet. This is the most you can do on the CPU. Get everything running at 100%. So the cooling, as it is, with the heat sinks, is sufficient for anything you want to do. "42 minutes. I did not mean to go 42 minutes, but I did. Okay, let's talk about problems, and I'll turn you loose. Class dismissed. Here's a problem. I'm logged in as Adams. Up here, see, I'm logged in as Adams. I installed network file system. Remember I talked about Bill Joy at UC Berkeley. He went off, and I think he was one of the co-founders, but he was, he had serial number 4. He had a one-digit employee number at Sun Microsystems, and while he was there, he invented and programmed the network file system, which allows me to share disk space between two systems. And I have another system, the gaming system, which I call JWST, because I'm doing some stuff on the James Webb Space Telescope, some physics stuff. And I share down here from my other system that's at this IP address. I store it here at temp. What I did is I'm sharing the file, and when I did that, I went to CD to temp, and it says I can't do it. And I do an ls -l on temp, and it's owned by Orange Pi, even though I loaded it. Well, maybe I didn't. Let's see let's try this. Sudo umount. Maybe it's a user error. Umount /home/Adam/temp. df. It's gone. Sudo mount 192.168.1.116. There's a whole bunch of administrative stuff that I've got to show you. So this is going to be a long series. Nope, that's an error. I mounted it. I should be owner. That is an error. Let's do one other thing. Sorry, keeping you, but this is hot stuff. Let's update my package information. This comes from a repo at IMHO Cloud, which means the manufacturer of the board has the distribution. I do not know if that means that Ubuntu has given up support for this. Something to experiment with, but I'll come back. So I'm going to do something here. I'm going to go away. I've got another orange pie on order. Should get it within 10 days or so. I'm going to set it up and I'm going to go through the other distributions, and I may do some on this one. By August 1st, which is, when is August 1st? Oh, it's Tuesday. No, I'm going to have to do it later. I'm going to get the system set up and we're going to get it working and not power it down. We're going to see what the mean time to failure is on this thing. It should be 20 years, but stand by. That's the plan. I'm going to get another one. I call this system Colossus. The new one's going to be called Guardian, from the movie Colossus, the Foreman Project in 1970. If you have not seen that movie, see it. I apologize. But then again, I don't apologize because I needed to cover this information. So your mission, if you choose to accept it, is to, one, get your system up and running. Hopefully it's an Orange Pi 5 Plus, or if you even have an Orange Pi 5B or one of the other ones, whatever single board computer you've got, go ahead and try this on it. I don't know if the Raspberry Pi can do 64-bit arithmetic. I've got one. Yeah, I've got one right here. No, I don't. I do, I don't. I don't. I think I sent it to the landfill. Okay. Enough. Look at there what I did. I went to another one. I'm going to let you go. Sorry. 45, 47 minutes. Hope it was entertaining. Hope you learned something. And we'll come back. My system is still at 100%. And it's interesting. We will watch the video. This video is done at 1080p, 30 frames per second. No. Yes. It's seems to be keeping up with it. The video on YouTube will show you if there's any hiccups during this process, and I'll have to watch it. The next video 7 is going to come back and do a summary of everything that I've done in the first 6 and fill in any errors and gaps and all that other stuff. And I have to make a decision whether I'm going to allow you to comment on my videos. Thank you. Talk to you later.